Hey everyone, and welcome. Today we're going to embark on a bit of an adventure, exploring the very heart of calculus. Our goal isn't just to learn formulas, but to truly understand why calculus works. Think of it this way. What is the fundamental problem that calculus was invented to solve? It's the problem of change. The world around us is in constant flux. The speed of a car isn't always the same. The population of a city grows year by year. The temperature changes throughout the day. For thousands of years, mathematicians were excellent at describing static situations, shapes, areas, volumes of perfect objects. But they were stuck when it came to things that were continuously in motion or changing in a non-uniform way. Calculus gave us the tool to analyze this motion and change. It's built on a remarkably simple yet powerful idea that we can use to handle the infinite. By the end of our talk today, you will be able to, first, use the concept of a limit to formalize our intuitive ideas about things approaching a value. Second, apply differential calculus to solve the tangent problem, which is a fancy way of saying we'll learn to find instantaneous rates of change, like the speed of a car at a single instant. And third, you'll be able to apply integral calculus to solve the area problem, which is about finding the area under a curve. It turns out this also allows us to calculate total accumulation over time, like the total distance a car travels. So are you ready? Let's dive in. We're going to start with the first big idea, the foundation upon which everything else in calculus is built. This idea is the limit. A limit in calculus has a very specific meaning. It describes the behavior of a function as its input approaches, but does not necessarily reach a certain value. Think of it like walking towards a doorway. You can get arbitrarily close to the doorway, a foot away, an inch away, a millimeter away, but you don't actually have to walk through it. A limit is about what value the height of that doorway seems to be approaching as you get closer. The mathematical notation looks like this. The limit as x approaches c of f of x equals L. This reads as the limit of f of x as x approaches c is L. What this means is that if we can make the value of f of x as close to L as we want, just by picking x values close enough to c, then the limit is L. So to recap, a limit tells us the value a function is heading towards. Let's look at a few examples. Our first example is about a simple, well-behaved function. This will help us build our intuition. Let's consider the function f of x equals x squared. We'll explore its behavior as x approaches 2. In other words, what is the limit as x approaches 2 of x squared? We can get a feel for this by plugging in values of x that are closer and closer to 2 from both the left side, values less than 2, and the right side, values greater than 2. Let's start from the left. If x is 1.9, f of x is 1.9 squared, which is 3.61. Closer at x equals 1.99, f of x is 39601. Even closer at 1.99, we get 3.996001. From the right side, at x equals 2.1, f of x is 2.1 squared, which is 4.41. At 2.01, it's 4.0401. And at 2.01, it's 4.0401. Looking at both tables, it's clear that as x gets closer and closer to 2, f of x is getting closer and closer to 4. We are approaching 4 from both sides. Therefore, we can confidently say that the limit as x approaches 2 of x squared is 4. For a continuous function like x squared, the limit at a point is simply the value of the function at that point. We just plug in. The limit as x approaches c of f of x is just f of c. This is a very useful shortcut for continuous functions. This is our baseline. Now let's explore a more interesting case where this simple rule doesn't apply directly. Our next example features a function with a hole in it. Consider the function g of x equals x squared minus 4 over x minus 2. The first thing you might notice is that if we try to plug in x equals 2, we get 0 in the denominator. That's a problem. The function is undefined at x equals 2, but what happens as we get close to 2? We want to find the limit as x approaches 2 of our function. Direct substitution gives us 0 over 0, which is an indeterminate form. It tells us we need to do more work. Let's factor the numerator. X squared minus 4 is a difference of squares, so it factors into x minus 2 times x plus 2. Now here's the crucial part about limits. Since we are interested in what happens as x approaches 2 but is not equal to 2, the term x2 in the numerator and denominator is never 0. Because it's not 0, we can legally cancel it out. This simplifies our expression to g of x equals x plus 2 for all values of x except for x equals 2. The graph of g of x looks exactly like the line y equals x plus 2, but with an open circle or a hole at the point where x equals 2. The point 2, 4 is missing from the graph. Visualize the graph, a straight line with a gap. As you walk along the line from the left or from the right, you're heading straight for the y value of 4, even though the function doesn't exist. At 2, the value it's clearly approaching is 4. So we say the limit as x approaches 2 is 4. This is the essence of a limit. It tells us about the intention of the function, where it's headed, regardless of what happens at the specific point in question. Limits don't always exist. Let's look at a function where the limit fails to approach a single value. Our third example is the piecewise function h of x. This function has two different rules depending on the value of x. Let's examine its behavior as x approaches 1. We want to find the limit as x approaches 1 of h of x. Because the rule for h of x changes at x equals 1, we need to consider the limit from the left and the limit from the right separately. These are called one-sided limits. The notation for a left-sided limit has a small minus sign, lim as x approaches 1 from the left. The notation for a right-sided limit has a plus sign, lim as x approaches 1 from the right. For the left-sided limit, we consider x values less than 1. So we use the rule h of x equals 2x. Plugging in x equals 1, we get 2 times 1, which is 2. For the right-sided limit, we consider x values greater than 1. So we use the rule h of x equals 3. The limit of a constant is just the constant itself. So the limit is 3. So from the left, the function approaches a value of 2. From the right, the function approaches a value of 3. These two limits don't match. A fundamental rule of limits is that for the overall limit to exist, the left-handed and right-handed limits must be equal. Since our one-sided limits are not equal, we must conclude that the limit as x approaches 1 of h of x does not exist. Visually, the graph jumps. There's no single doorway the function is walking towards. It's approaching two different heights from opposite directions. So the limit does not exist. Okay, that's our look at limits. Let's recap what we've learned. We learned that limits describe the intended destination of a function. We saw that for a continuous function, the limit is simply the function's value. We also saw that for a function with a removable discontinuity, a hole, we can find the limit by algebraic manipulation. And finally, we learned that for the limit to exist, the function must approach the same value from both the left and the right sides. Now, let's do a practice problem to make sure these concepts are solid. Pause the video and try to find the limit as x approaches 3 of x squared plus x minus 6, all divided by x plus 3. Good luck. Welcome back. Let's walk through the solution together. First, we tried direct substitution. Plugging in x equals 3, we get 3 squared plus 3 minus 6 in the numerator and 3 plus 3 in the denominator. This simplifies to 9 minus 3 minus 6, which is 0 divided by 0. An indeterminate form. This tells us we need to factor and simplify. The numerator is a quadratic. We need two numbers that multiply to 6 and add to 1. Those numbers are plus 3 and 2, so the numerator factors into x plus 3 times x minus 2. Now our expression for the limit becomes the limit as x approaches 3 of the product of x3 and x2 divided by x3. We can cancel the x plus 3 terms because we are looking at the limit as x approaches. Such 3, meaning x is not equal to 3, so x plus 3 is not 0. This simplifies to the limit as x approaches 3 of just x minus 2. Now we have a continuous function. We can use direct substitution. Plugging in x equals 3, we get 3 minus 2, which is 5, and that is our final answer. The limit is negative 5. Excellent. We've now established a solid footing in the world of limits. This foundation will be essential for the next two big ideas in calculus. We just saw that limits help us understand where a function is headed. Now, let's put that concept to work on one of the most fundamental problems in all of mathematics: finding the tangent line to a curve. This might seem like a niche problem, but its solution unlocks the ability to calculate instantaneous rates of change, which is the heart of what we call differential calculus. By the end of this section, you'll be able to calculate the slope of a curve at any single point. So, what's the big deal about a tangent line? A tangent line touches a curve at only one point, and it has the same slope or steepness as the curve at that exact point. Finding its slope tells us the rate at which the function's output is changing at that precise instant. For example, if the curve represents the distance a car has traveled over time, the slope of the tangent line at any point would represent the car's speed at that exact moment. This is instantaneous velocity. The problem is, the basic formula for slope needs 2 points. How do we find the slope using only 1 point? The formula you learned in algebra is slope equals change in y over change in x. This formula relies on having 2 distinct points, x1, y1, and x2, y2. But a tangent line only touches at 1 point. This is where our new tool, the limit, comes in. We'll use a sneaky, brilliant trick. We'll start by finding the slope not of the tangent line, but of a secant line. A secant line connects 2 points on the curve. This is a slope we can calculate with our old formula. Let's fix 1 point, let's call it P, and let's pick another point, Q. We can calculate the slope of the line connecting P and Q. Now, here's the magic. We're going to make that second point, Q, slide closer and closer to our fixed point, P. As it slides closer, the secant line gets steeper or flatter, evolving, until it becomes the tangent line itself. In calculus terms, we are taking a limit. The slope of the tangent line is the limit of the slopes of these secant lines as the 2 points merge into one. This formal statement is the foundation of differential calculus. We are using a limiting process to get an exact value, an instantaneous rate of change. To formalize this, let's derive the main formula. We have our curve y equals f of x. We are interested in the slope of the tangent at a specific point. Let's pick our first point, P, with coordinates x and f of e. For our second point, Q, we'll start at x, and then move a small distance h to the right. So its x-coordinate is x plus h, and its y-coordinate is f of x plus h. First, let's find the slope of the secant line connecting P and Q using our old slope formula, change in y over change in x. The change in y is f of x plus h minus f of x. The change in x is x plus h minus x, which is just h. So the slope of the secant line is this expression, f of x plus h minus f of x, all divided by h. This formula tells us the average rate of change between x and x plus h. But we want the instantaneous rate of change right at x. Remember the sliding point Q? As Q approaches P, the distance between them, h, shrinks to 0. So, to find the slope of the tangent line, we need to find the limit of our second slope as h approaches 0. The slope of the tangent line, which we call the derivative of f at x, is defined as the limit as h approaches 0 of f of x plus h minus f of x all over h. This is one of the most important formulas in all of calculus. It's called the definition of the derivative. We've taken an intuitive idea of a tangent line and built a rigorous mathematical definition for its slope using a limit. This slope, the derivative, is the instantaneous rate of change of the function. So, the derivative is 2 things. It's the slope of the tangent line at a point, and it's the instantaneous rate of change. Now let's apply the definition of the derivative to a function. This is where we will use the limits we learned earlier. Let's find the derivative of f of x equals x squared. We start with our definition. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. First, let's find the piece f of x plus h. We replace every x in our function with x plus h. Since f of x is x squared, f of x plus h is x plus h squared. Expanding this, we get x squared plus 2xh plus h squared. Now we plug this and f of x back into the definition. F prime of x equals the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared, all divided by h. Let's simplify the numerator. The x squared term and the negative x squared term cancel out. This leaves us with the limit as h approaches 0 of 2h plus h squared over h. Notice that every term in the numerator has an h. This is by design. We can factor out an h from the numerator. This gives us the limit as h approaches 0 of h times the quantity 2x plus h over h. Now for the cancellation step. Since we're taking the limit as h approaches 0, but h is not actually 0, we can cancel the h in the numerator and denominator. This simplifies to the limit as h approaches 0 of just 2x plus h. Now we have a simple limit to evaluate. We can use direct substitution for h. Plugging in h equals 0, we get 2x plus 0, which is just 2x. This is our derivative. The derivative of f of x equals x squared is f prime of x equals 2x. This formula tells us the slope of the tangent line to the parabola y equals x squared at any point x. For example, the slope at x equals 2 is f prime of 2 equals 4. The slope at x equals 0 is f prime of 0 equals 0, which makes sense as it's the bottom of the parabola. The derivative is a function that gives us the rate of change at any point. That was a lot of algebra. Fortunately, there's a pattern, which mathematicians figured out and condensed into a set of rules. The first and most important rule is the power rule. This rule tells us that the derivative of x to the power of n is n times x to the power of n minus 1. It's an incredible shortcut that allows us to bypass the messy limit definition every time. For our last example, let's find the derivative of f of x equals x to the 6th power. Using the power rule, n is 6. So the derivative is 6 times x to the power of 6 minus 1, which is 6x to the 5th. It's that simple. Now this derivative, 6x to the 5th, is itself just another function. Its derivative is called the second derivative. We can find it by applying the power rule again. The derivative of 6x to the 5th is 30ex to the 4th. The second derivative tells us about the concavity of a function, whether it's shaped like a cup pointing up or a cup pointing down. Let's do one more. The derivative of x to the 100th is 100x to the 99th. Imagine doing that with the limit definition. This shortcut is why calculus is so powerful in practice. Recap. We started with the definition of the derivative as a limit of secant slopes, which gives us the slope of the tangent line and the instantaneous rate of change. Then we saw the power rule, a tool for rapid calculation. You can now calculate the derivative of any power function. We've conquered the tangent problem, which leads us to differential calculus. Now let's switch gears to the other great problem of calculus, the area problem. This problem asks, what is the area of a shape bounded by a curved line? If the shape is a simple rectangle or triangle, we have formulas. But if one side is a curve, it's not so straightforward. Just as the derivative allowed us to find instantaneous rates of change, solving the area problem will allow us to find the total accumulation or sum of a changing quantity. For instance, if the curve shows the speed of a car over time, the area under the curve between two times represents the total distance the car traveled during that interval. How do we solve this? Again, we use a limiting process. We'll start with an approximation and then make that approximation perfect. Instead of finding the area of the curved shape directly, we'll approximate it using a shape we do know how to measure, a rectangle. We'll divide our time interval from A to B into several smaller subintervals of equal width, which we'll call delta x. On each of these subintervals, we'll draw a rectangle. The base of each rectangle has width delta x. Its height will be the value of the function somewhere in that interval. We could pick the height from the left side, the right side, or the midpoint. The area of each rectangle is its height times its width. If we sum up the areas of all these rectangles, we get an approximation of the total area under the curve. The more rectangles we use, the better the approximation will be. To get the exact area, we let the number of rectangles n go to infinity. As n gets infinitely large, the width of each rectangle, delta x, becomes infinitely small. The sum of the areas of these infinitely many, infinitely thin rectangles gives us the precise area. The limit as n goes to infinity of this sum is called a definite integral. This is how we use a limit to go from a rough approximation to a perfect calculation of area. Just as with derivatives, we don't always want to compute this messy limit for integration. Fortunately, there is an incredible shortcut, the other great theorem of calculus. It connects the area problem to our earlier work on the tangent problem. It's called the Fundamental Theorem of Calculus. This theorem states that to find the exact area under a curve, you can use an antiderivative. An antiderivative, denoted with a capital F, is simply a function whose derivative is the original function, f of x. The Fundamental Theorem of Calculus says that the integral from a to b of f of x dx, which is the area we are looking for, is equal to f of b minus f of a. This means you find any antiderivative of f, evaluate it at the top limit b, evaluate it at the bottom limit a, and subtract. It's a miracle. We can find area without rectangles or limits. To put it simply, integration, area, and differentiation, slope, are inverse processes. If you take the derivative of a function, you get its rate of change. If you integrate that rate of change, you get back to the original function. Let's see this in action. The antiderivative rule for power functions is the inverse of the power rule for derivatives. To find the antiderivative of x to the n, you raise the power by 1 to n plus 1, and then divide by that new power, e. The plus c is a constant of integration. We'll ignore it for now as it cancels out indefinite integrals. Using our formula, the antiderivative of x cubed is x to the fourth divided by 4. This is often written in square brackets. Now we apply the theorem. We plug in the top limit, 3, and subtract the result from plugging in the bottom limit, 1. This simplifies to 81 over 4 minus 1 over 4, which is 80 over 4, or 20. The exact area is 20. Let's do 2 more quick examples with the Fundamental Theorem of Calculus to reinforce the idea. Let's find the integral from 0 to 2 of 4x squared d. First, we find the antiderivative of 4x squared. The constant 4 just comes along for the ride. The antiderivative of x squared is x cubed over 3. So our antiderivative is 4x cubed over 3. Now we evaluate this from 0 to 2. We get 4 times 2 cubed over 3, minus 4 times 0 cubed over 3. This simplifies to 4 times 8 over 3, which is 32 over 3. The area is 32 through 3. Now what if the area is below the x-axis? Let's consider the integral from 0 to 4 of 2x minus 4d. The graph of y equals 2x minus 4 is a straight line. Between 0 and 2, the line is below the x-axis. Between 2 and 4, it's above the x-axis. Let's see what the FTC tells us. The antiderivative of 2x minus 4 is 2 times x squared over 2, which is x squared, minus 4x. So our antiderivative is x squared minus 4x. We evaluate this from 0 to 4. Plugging in 4, we get 4 squared minus 4 times 4. Plugging in 0, we get 0 squared minus 4 times 0. This is 16 minus 16, which is 0 minus 0. The result is 0. The integral came out to 0. Why? Because the FTC calculates signed area. The area below the x-axis counts as negative. For this specific line and interval, the negative area between 0 and 2 exactly cancels out the positive area between 2 and 4. The net area is 0. This highlights that the Fundamental Theorem of Calculus is more than just an area calculator. It's a net accumulation calculator. Let's put your understanding of the area problem and the Fundamental Theorem of Calculus to the test with a practice question. Go ahead and pause the video and calculate the definite integral from 0 to 2 of x cubed minus x dx. Welcome back. Let's work through this one. Our strategy is to find an antiderivative and then evaluate it at the limits of integration. First, let's find the antiderivative of x cubed minus x. For x cubed, we use the power rule, so we get x to the fourth over 4. For x, which is x to the first power, we get x squared over 2. Our antiderivative is x to the fourth over 4 minus x squared over 2. Now we evaluate this antiderivative from 0 to 2. We apply the fundamental theorem. Plug in the top limit, 2, then subtract the result from plugging in the bottom limit, 0. This gives us 2 to the fourth over 4 minus 2 squared over 2 for the first part. And for the second part, it's just 0 to the fourth over 4 minus 0 squared over 2. Simplifying the first expression, 16 divided by 4 is 4, and 4 divided by 2 is 2, so we have 4 minus 2. The second expression is simply 0 minus 0, which is 0. Finally, 4 minus 2 is 2. The value of the definite integral is 2. This means the net area under the curve y equals x cubed minus x between x equals 0 and x equals 2 is 2. Even though part of the graph is below the axis, the positive area outweighs the negative area. We've covered a lot of ground today, but I hope you now see how these seemingly disparate concepts, limits, derivatives, and integrals, fit together to create a cohesive and powerful framework for understanding the world. Calculus works because it allows us to handle the infinite with precision. The world is full of continuous change, and calculus provides the tools to describe it with equations, predict it with models, and solve complex problems in every field of science, engineering, economics, and beyond. Let's quickly recap our journey. We started with the limit, the idea of approaching a value. This allowed us to build the derivative, which represents the slope of a tangent line and the instantaneous rate of change. On the other side, the limit of a sum led us to the integral, which represents area and total accumulation. The magic that connects them is the fundamental theorem of calculus. The derivative is about finding the slope. The integral is about finding the area. They are opposites, and this relationship is why calculus is so effective. You now have a conceptual understanding of why calculus works and the key problems it was designed to solve. It's a beautiful system built on simple yet profound ideas about the infinite. Thank you for joining me on this exploration. I encourage you to keep asking why as you continue your journey in mathematics. Keep learning, and I'll see you next time.